Hello, can you hear me? So I just went straight live tonight. Sorry I'm a little bit late. I was doing a little bit of few minutes of last minute research, but I decided to look into some of the more interesting planets that we have discovered over the years, and I figured I would go through that. So I'm going to start off with a brief introduction, and then I'm going to go back through and go into a little bit more detail about each one. So the first one that we have tonight is called the TRAPPIST 1 system, and it is TRAPPIST 1 B-H. It is known for 7 rocky, Earthish sized planets around a very cool red dwarf. Several are in the star's habitable zone, making this one of the best targets for atmospheric studies. And then next, we will have Proxima Centauri b, the closest known exoplanet to the solar system, and it is an important benchmark for studying habitability around an M dwarf. And then we get into the more complicated names, such as HD 40307 planets, a quiet multi planet system with several likely rocky worlds, including some super Earth sized ones, notable for how many compact planets it has. And these are the systems in some of these. Now we're getting into systems with some of these. Then we have Kepler 186f and the Kepler 186 system. Among the first Earth size in the habitable zone, finds that got a lot of attention, good for thinking about what Earth like might mean statistically. So, this would probably be a good candidate if we were to look for other planets that would be able to maintain life in a similar fashion as to Earth. And then we have Kepler 452b, often called a near Earth's twin because it orbits in a habitable zone like region around a star similar to the sun. Still not truly Earth-like, but it is quite compelling. Now, WASP 121b is a hot Jupiter with extreme temperatures and evidence of atmospheric chemistry that can include exotic species, great for learning how atmospheres behave under intense irradiation. And it says exotic species, which sounds to me like they found life on another planet. That's interesting. And it says it's great for learning about irradiation, which would also be interesting to see what kind of life could survive in radiation, because we have some of that here on Earth, like the Chernobyl incident and all the dogs and fish and all those that are able to survive in that. They were able to, mutate over the years and they were able to survive. So it would be interesting to study them, I believe. I think it would be. And then we have WASP 39b, a benchmark transiting planet for atmosphere work. Its size and signals make it a frequent target for telescopes studying exoplanet atmospheres. And then, last but not least, we will be looking into GJ 1214b, which is a mini Neptune or sub Neptune world that's famous because its atmosphere appears hard to pin down, and it would be helpful for understanding how common thick and featureless atmospheres might be. So, this is what we're getting into tonight. Oh, hey, James. Good to see you tonight, old 8 gauge. Sorry about that. I just got in. Uh, don't believe it till you physically see it. I can agree with that. That makes sense. You got to see evidence before you believe in something. Sunglasses? I'm just having fun. I like my sunglasses. The room's a little bright tonight. Just having some fun with it. I think they make me look pretty cool. That they give me confidence. How about that? They give me confidence. All right. So we're going to get into each of these a little bit more. So first off, let's start with the TRAPPIST 1 planet. So we're going to get into this, and it is basically kind of like a failed Venus in spirit, okay? It likely experienced strong heating and volatile loss early on and may have a very thin or no current atmosphere, according to what we know about it. So the day side is expected to radiate heat brutally fast. If it had water early, the current picture is more steamed or stripped than ocean world. It's also a great example of how a planet can be rocky and still be a bad place, because atmospheres are the difference between hottest desert and maybe habitable. Now, the TRAPPIST 1 1C, that was B, which it was the innermost. Now, the C area is still too hot. Hello, Haley. Good to see you tonight. Thanks for coming in to chat with us. We are talking about some of the most interesting planets that we've discovered out here tonight. And then we got the TRAPPIST 1C, which is still too hot for our normal survival, which is a challenge, of course, in relation to the atmosphere. It is similar moral to B, which is the failed Venus that we were talking about a moment ago, but with the slightly more favorable odds. The climate outcomes depend heavily on whether any atmosphere was retained and how efficiently it could redistribute heat. With tight irradiation and tidal locking, even small atmospheric differences can produce huge swings in whether the night side stays frigid if it was airless or moderated if it had an atmosphere. And then we got a few more, but I don't want to spend too much time on any one, so we're going to go ahead and go to the next one from there. But to summarize, TRAPPIST 1 isn't just a set of planets, it's an experiment testing whether terrestrial worlds can keep atmospheres and water when the star is hostile and the orbits are tight. So, next up, we're going to be talking about Proxima Centauri b, which is the habitable zone. Sorry, I don't know why that is such a difficult word for me tonight. Next door, but the star is a little bit complicated. Now, what makes it extreme is that it orbits a nearby M dwarf, so it's relatively easy to observe. The M dwarfs can emit energetic radiation and frequent flares, which threatens the atmospheres, especially for planets close enough to be in the habitable zone. So it sounds kind of like the sun almost, because the sun emits a lot of radiation flares too, I believe. Like frequency flares and energy stuff, all that. You know, I'm probably not using the right words, but I feel like I know what I'm talking about. Now, the habitable zone for an M dwarf is also tricky because the star's early life can be more intense, affecting whether a planet arrives with water in the first place. Because if water gets close to something and it's too hot, that can affect it and that could turn it into steam and get rid of any life that was in it. Now, what Proxima b could realistically be is it might actually be the poster child for any potential ocean world, but the key question is whether or not it has atmospheric survival potential. But we are not really sure at this point in time. Now, the WASP 121b is an ultra hot atmosphere where chemistry gets a little bit weird. It's interesting because we say that it's basically like a hot Jupiter. It's not potentially habitable, but it is extremely informative. It's basically a laboratory for how planets behave when their atmospheres are strongly irradiated. So over here we have, like I mentioned a minute ago, we had Chernobyl, which is like highly irradiated. Imagine a whole Chernobyl planet. So that's why they want to study it so badly, because it's basically a whole entire planet just filled with radiation. Thank you for the subscription, Nick. Thank you for subbing. Good to see you tonight. Good to have more people in the chat with us, always. Thank you for commenting. Thank you for the sub. We're talking about some of the more interesting planets we got out here tonight. Now, the WASP 121b is ultra hot and strongly irradiated, which is a terrible combination for life, obviously. But what we can learn from it is it's so hot that standard molecules can shift into unexpected abundances. So if we were able to learn how to do that, we might learn a way to use this planet for some sort of production if we were able, to get out into outer space travel at some point in the future. A hot Jupiter's atmosphere can develop strong day night temperature gradients. Whether there's an efficient wind circulation pattern or strong thermal inversions affects which spectral features we might potentially see. The planet's extreme environment makes it easy to detect atmospheric signatures with transmission emission spectroscopy. So that's pretty interesting. It basically teaches us the physics of atmosphere under maximum stress, which matters because the same atmospheric process, such as composition, heat transport, clouds, hazes, and escape, ultimately determine whether small rocky worlds can have stable climates. And if we wanted to have stable climates, that would definitely be important for, any sort of future life and even for experimenting because we would need to have a stable climate for a controlled experiment, I believe. And to answer, Haley in the comments said that Chernobyl is safe now. I had not heard that, but that is good to hear. Thank you very much for letting us know. I will just take your word on that until someone corrects us because I actually found out the other day there's actually a psychological effect. I forgot what it's called, but there's a psychological effect where if you give out the wrong information, you're more likely to get the correct information in reply correcting you than if you just ask someone what the right information is. So I think that's pretty funny. But as we always say here, always do your own research. Make up your own mind. Don't just take our word for it. Do your research and make up your own mind about everything that we say here. Now, next up, we're going to get into Kepler 452b, which is near Earth by analogy, but not by equivalence. What I mean is, it's still very much an exoplanet with its own identity, especially because habitable zone is an evolving boundary definition. The planet's actual radius and mass constraints can suggest a bulk composition that is not necessarily Earth like, and it's more like a sub Neptune, then the surface question changes completely at that point. Even with a rocky planet, tidal heating is usually not the dominant factor compared to close in systems, but stellar evolution over time can still shift conditions. So essentially, it is Earth like because of the geometry, which is appealing, but the composition and climate remain to be the real gatekeepers here. And then we have something called HD planets, which is a very interesting system to me just because it's called HD. The HD 40307 planets. These are the ordinary multi planet systems that could still be worlds. So essentially, they have potential. Now, what makes these interesting is that it demonstrates the compact multi-planet architecture which can occur around relatively nearby stars, and it includes planets in a range of sizes that may include rocky ones. The story here is about the system architecture. The multiple planets suggest a disk-driven formation pathway where stable niches exist. So, like in between the rings of a disk-driven planet is where these would exist. So for the habitability, whether or not, life could form there and whether or not we could survive there and habitate such a planet, you still have to consider stellar activity and the planet's true composition. But multi-planet systems can also mean gravitational interactions that change long-term climate-relevant properties, like eccentricity histories. Sorry. So basically, we're talking about how many potentially rocky planets could be out there. Not just one spectacular, crazy planet, but how many potentially rocky planets may be out there. Not anything else, just, whether or not they're rocky. So, next up, we have the HD 189733b system, which is a blue scatterer hot Jupiter in terms of, well, that's what the typical scientific community refers to it as a descriptor. What that means is it is a benchmark exoplanet in atmospheric work, which means it is bright enough relative to many targets and frequently studied. So they study it a lot because it's bright. Okay? That's pretty much what it boils down to. Now, in terms of what it is, in why they call it a hot Jupiter, it is often discussed in the context of aerosols and clouds and how scattering can shape observed colors and spectra. So something you might see in, you know, uh, I don't know, Invincible, because they do a lot of fighting in outer space when they like separate those clouds and stuff. That's kind of what they're talking about there. And, the different colors and spectra and all that other stuff that you might see when that happens. So, one way you could interpret it is an example of how atmospheres can be dominated by particulates and chemistry rather than just the gas phase molecules. This is what makes the atmospheric science tangible. The planet's look and spectrum are fingerprints of particles, circulation, and chemistry. And then we got a couple more, but we're going to skip over those because there's a lot in those. So, you know, that's basically where we're at. And then I thought, wouldn't it be fun if I tried to make like a short little story about how each of these planets may have formed? But I thought that would be a little too much, you know, and I just wanted to keep it basic to the facts. So that's all I got for you tonight. Sorry it's a shorter episode. Yeah, but I hope you enjoyed learning about some of these more interesting planets we have out there. And, definitely always look to the stars because we never know what's out there. And we may not know, anything too overly interesting right now. It's still pretty boring right now, I'll be honest. But we have some stuff to look forward to in the future because I think, you know, one thing I've never understood, and just before we end, one thing I've never understood is why we're so obsessed with going into outer space when we still have so much left to explore at the bottoms of our oceans. We need to go inwards, not outwards, as they say in the spiritual community with meditation. I think we need to look at the bottoms of our oceans and inside our mountains and inside our earth before we go out. But thank you. And Haley in the chat said that you should be able to see Jupiter and Venus with the naked eye tonight. So that's pretty interesting. And I did see something out there earlier. I was wondering what that was. So thank you for letting everyone know. And as always, stay uncanny. We will see you next time. Thank you.